Good afternoon, everyone. Okay, so I didn't expect so many people are here. Must stand here? But it's hard to see. Can I stand here? I think it's okay. You will record the sound. Okay, so my name is Lee, and on behalf of my supervisors and members, today I'm going to present my research in implementing a data-driven simulation method for quantifying pipe welding operator performance. So here is the content of my presentation: introduction, rationale, research objectives, methodology, applications, and contributions. Okay, so I will start with introducing the industrial construction. So industrial construction is a method which uses prefabrication pre-assembly. So examples include petroleum refineries, petrochemical plants, oil and gas production facilities. And pipe fabrication is the most important process of the industrial construction. And typically it involves parting, fitting, welding, and quality inspection processes. So for pipe welding, each pipe weld involves different design attributes. And here I listed all of 4 of them. And the first one is nominal pipe size. As you can see in the figure, the nominal pipe size represents the interior diameter of the pipe. And pipe schedule is not the schedule planning of that schedule. This schedule means the thickness of this pipe. And material, typically it involves 4 types of material. First one is plain carbon steel, alloy steel, stainless steel, and others. And the last one is weld type. And as you know, when you weld a pipe, you may like hot weld, fitted weld, and other types. So you can imagine that what number of combinations can be generated based on those 4 types of pipe attributes. And also, variable operator quality performance make this process more complex to predict. And now I will talk about welding quality inspection in detail. So pipe welds are inspected and sampled via non-destructive examination recorded in the year. And they use sample fraction nonconforming to infer the population quality performance of this type of pipe weld. So it is defined as the non-conforming items over total inspected items. It's pretty easy to understand. It's like if you do 100 pipes and 10 of them fail, then your fraction non-conforming is 10%. We can also call it repair rate. So nowadays, companies, they are using computer-based quality management systems to do all those quality control processes because it's required by ISO 9001. And in our research, we are collaborating with multiple companies. And now I will just describe the problem from one company. And they are using the quality control system called Abstract. And this system was developed by University of Alberta from our group 10 years ago. And it tracks 10 years pipe welding in quality inspection data. And there are more than 250,000 ND inspection records tracked in this system. And if you look into the data, there are more than 680 attribute combinations. As I said, those combinations are from these 4 design attributes. So, although the system has facilitated the collection of vast amounts of project quality management data, it still lacks descriptive capabilities to accurately and reliably estimate operator quality performance. So, the practitioner has the problem of converting this data into useful information. So basically, they ask us what data sources are useful for inferring the quality performance of different operators, and how to transform real-time multi-source data into interpretable data, and how to incorporate inspection sampling uncertainty using those data we track. And finally, we want to know which operators have exceptional quality performance in their company. So practically, a more capable, analytically based decision support system is needed to improve quality-related decision-making processes. The system must generate reliable and accurate quality real time, and the system must reduce data interpretation for practitioners. So there are also gaps in the academia. So based on our literature review, we found that following gaps exist. So the first one is a quantitative fraction non-conforming estimation method that can incorporate operator performance uncertainty and well attributes has not been investigated. The second one is that a dynamic simulation environment that can recalibrate elements in real time has not been developed in the construction simulation domain. So the proposed research will attempt to address following gaps through completion of this research. So overall, this research aims to quantify operator welding quality performance by implementing a data-driven simulation approach. This approach will fuse and transform data from separate data sources into integrated data. And this research will also implement an MCMC-based approach to numerically estimate the posterior distribution of operators' welding quality performance. And finally, this research can help identify potential applications to comprehensively improve pipe welding quality performance. So here is the framework of the methodology. It contains 4 components. The first one is data source, the second one is data adapter, the third one is data analysis module, and the fourth one is decision support module. So the idea behind this methodology is that real-time data are collected and fed into the simulation model to help the original simulation model to generate more accurate and predictable results. And all those steps are conducted by using R. R is a free computing programmable software, and it's free and it's pretty strong, powerful. There are more than 10,000 packages now available for you, and it covers all advanced statistical methods, machine learning methods, data mining methods, and simulation methods. So now I will talk about details about data source. So as we know, multi-relational databases can often provide richer information for data mining and therefore achieve better outcomes. That means useful information is dispersed in various tables from different databases. So in this research, we use 2 data sources. The first one is a quality management system called AppTrack. It has been implemented by KBR for 10 years. And second one is engineering design system. It's all the best in work. Everybody's familiar with this. So the information from the quality management system are NDE inspection results, weld type, include bottom weld, fitted weld, and other types, and welder information. And information from the engineering design system, there are weld design attributes like the NPS, that's the internal diameter of pipe, and schedule, that's the thickness of pipe, material information, and I mentioned that 4 types of materials. So the second step is to develop a data adapter. A data adapter integrates real-time information from various data sources into one centralized tidy data set. So as we can define, in a tidy data set, each variable is saved in its own column, and each observation is saved in its own row. Only after obtaining this type of data, we can perform more advanced data mining tasks. And why we need this? Because we need to perform real-time computation. And originally, our simulation research are based on the historical data. We just collect data. We use this data to construct our simulation model. But we don't consider the real-time information from the actual system. We don't update the simulation based on any real-time information. That's the drawback of the original simulation. So here we will solve it. So this data adapter mainly contains 3 functionalities. The first one is data connection. So we use RODBC package from R, and it can do all types of data connection to all types of databases. And data wrangling, we use DPLYR and TidyR packages from R as well. And data cleaning, this is to help us remove the missing values, noise, and inconsistencies. So this is a data analysis module. So in our research, a data analysis module is comprised of a suite of algorithms that can facilitate the establishment of metrics for decision support. So for this specific problem, we have three algorithms embedded in this data analysis module. The first one is fraction non-conforming modeling. So this one will abstract the real quality inspection problem into a mathematical model. So basically, we use Bernoulli random variable to model the process, and this variable can be fitted as a binomial distribution. And the second algorithm is the metropolis casting algorithm. It's a specialized type of algorithm from MCMC method. And the capability of this method is that it can be used to generate numerical approximation for any type of distributions. But here, we just use it for fraction non-conforming distributions. And it can recalibrate input models using real-time data. Basically, when new data are collected, it can be fitted into the data analysis model, and new distributions will be generated based on the new data. And the third one is the visualization part. Basically, we utilize the result generated by the metropolis casting algorithm to generate the posterior distribution and the box plot of the fraction non-conforming for a certain type well. So decision support. Here, I will give you a simple example to illustrate what can we do based on this research. So, as you can see, we selected a type of pipe which is the standard thickness and 2-inch diameter, and the material type is A, which is plain steel and barbell. And we investigate all those data, and we just selected the top 17 operators whose inspection records are exceed 100 times to make the result more statistically significant. So as you can see, the range of those 17 operators are from, like, this one is around 15%. That's the repair rate of this well for this type of work. And the best one only around 5% repair rate. So that means different people, they do have different performance for the same type of work. So from the visualized output, practitioners can infer operators' skill level for specified type of work. And they can identify operators who consistently produce high-quality wells. And they can also use this to support future decision-making processes. Here, I gave you 3 potential applications of this research. The first one is production planning. So we can use this research to allocate welding work to operators with highest performance quality for the particular well type, and directly improve the overall welding quality performance. The second one is that we can use it for employee training. We can determine which operators are most proficient for each type of well, and we can ask them to demonstrate their operation processes and share their professional knowledge for employee training purposes. Then the third one is strategic recruiting. So we can investigate the high-performance operators' profiles and conduct data-driven recruiting to hire qualified welding operators. This will help the company improve their quality performance largely. So contributions. From the academia side, this research developed a dynamic simulation environment using R, and this research also created advancements in simulation and data analytics. First one is real-time measurements recalibration. The second one is complex probability distribution approximation using MCMC method. And this research also provided a novel Bayesian statistics-based approach for fraction non-conforming uncertainty modeling. And from the industry side, we developed a welder quality performance quantification system to improve their quality in related decision-making processes. Reference? That's it. Thanks.